then is important to study and understand. And the vector bundles on that. When I say vector, it's a smooth manifold, so I need the smooth vector bundles, of course. The first examples that we've discussed already of course are the tangent bundle and the associated cotangent bundle, and the bundle of bilinear forms I call it Bilin of the tangent bundle. That's a horrible notation, but let's live with it for now. So we have the smooth structure of these bundles. It's simply given by frames. For example, if you have the tangent bundle, then you look at the tangent bundle on an open coordinate neighborhood. So we have an open coordinate neighborhood, and we have the tangent bundle there, and we have the frame there. We have a frame which quite often I call E. So the frame is called E. Maybe in text, maybe make it a little bit fat. E1 through En. What that means is that EI maps U into the tangent space is really a section over U. So it's a moving tangent vector, a section, all I equals 1 to all I. And in fact here, in this case, we write EI is just the partial derivative operator ddxi, which is a derivation on smooth functions, and this is denoted by delta I. So that is a frame, and that gives you a smooth section. So locally, a smooth section is given by S equals SI EI. So this maps U into the tangent. In general, the space of global sections gamma, I'll try not to make a mistake now. Okay. The sections over the base of the vector bundle E. Yeah. The space of global sections. Of global sections. And we know that, for example, for the tangent bundle, we know what that's called. We know the global sections very well. A global section here is a vector field. This is all review. So that's one important bundle, and another important bundle is the cotangent bundle. And you take the dual frame, and the dual frame is given by, maybe by f. I use f for function, f1 through fn. And the fi's are just dxi's, the dual bases at each point. So we don't have to do any more thinking, because once we start with a tangent bundle, we just take the dual bundle and dual frame, the dual. So locally, omega, one form, is a linear combination. It's a section of the cotangent bundle. And locally, the one form is just a linear combination over the functions fi and xi. What's clear here is that in general, you can always multiply by a function. So in general, you can always multiply by a C infinity function. This thing, the space of sections, over a base, a smooth manifold of a vector bundle E. Maybe let me emphasize we're always dealing here in this class, but I'll write it here once. C infinity sections is a module in a natural way over the ring. So if we call this thing module, well, I will call it a module over the ring. So these words in algebra I've talked about, ring of C infinity functions. So in general, recall if you have a ring and a module, you have this multiplication map that makes sense. It's just like a vector space, except the coefficients are now functions in our case, or anything in general. So this is the module structure of this thing. Completely clear. If you have, for example, a vector field, on M, and f a function. So this is the basic example that we thought about. Then you could multiply the function times the vector field, and it's still a vector field. So that's the setup that we have in manifolds. The vector fields in one form. And thinking about geometry a little bit, we go to bilinear forms. First of all, on a vector space, then I will recall this bundle of vectors. So what is a bilinear form on a vector space? It's a mapping which is linear. So over the real numbers, everything is here over the real numbers. So this is linear in both arguments. You tell your little sister or brother at home about this course, you say, well, the first thing we looked at was if you have a vector AB and a vector CD, and this is the vector V, and this is maybe U, and this is the vector V, then the standard bilinear form on R2 of UV, you know what we usually use, is AC plus BD. But you cannot assume this in physics or mathematics, because you do not have a canonical linear diagonalization of your form, and the eigenvalue is always playing a role, so you just want to deal with abstract bilinear forms. So a basis, so if I say let B of V, well, let's call it bilinear of V, to be the bilinear forms on V. On B, and I take one of these guys, and I want to understand it, then we want to express this in a basis. B in a basis, and of course later in a frame. So you want to know what to do, and I just want to remind you what to do. If you have a basis E, now basis, this is a basis, but it's not moving, so it's just a basis of V, Then there's some basic bilinear forms that you know about. So the basic bilinear forms coming from the basis, basic forms that even my grandson would think about at age 5, are the forms Vij associated with this thing, which we call EI tensor EJ, Fi tensor Fj, where F1 through Fn is the dual basis. Now I know you don't have that much experience with tensors, right? You have some, but not that much. But this is just notation. This is just notation. This doesn't mean anything. Right now it's just notation. So what it means is that Vi, so if you have a vector U, which is Xi Ei, and V, which is Yi Ei in this basis, then B of this vector UV, of these pairs, well, it's B of the sum, Xi, well, I should write two different things here, J, Xi, Ei, Yj, Ej, and it's bilinear. So it's Xi, Yj times B of Ei, and Ej. Yeah. And this form, Bi, Fi, so, and this is, okay, and B of, okay, fine, period. Period. And I call this, say, Bi, well, I'll just leave it at that. And so, we define Fi tensor Fj and Ef of Ei, Ej to be 1, well, let's say K and L. It's, well, I don't know. Delta I, J, K, L. You have to get used to this terrible physics thing. You guys in physics make me crazy, right? So this thing is only, it's 1 or 0, but it's 1 when you have I equal to K and J equal to L, right? So it's, right? Okay, no big deal, right? Yeah, you just, so that means that is equal to that, and that equals to that, and that's the usual notation. So what you see is that Bij B is equal to B of Ei, some whatever B of Ei Ej is, times Fi Fj, and that's some number, whatever it is. Let's call it Bij Fi. It doesn't make any difference. These are the basic things. It says then that Fi Fj is the basis. Fi tensor Fj is the basis for the bilinear forms. I know you don't like this notation, I don't like it either, but if you have a bilinear form, you have a basis, then you go to the dual basis, and you have these special bilinear forms which do almost nothing. They kill everything except if it's just right. They don't kill I, Ej, you get one there. There it is. Okay? Okay. Fine. So that says that if you have a frame for the tangent bundle, and then you go to the dual frame for the cotangent bundle, these things giving you the smooth structure, because these are this is giving you the smooth structure. Then you go to the associated frame of tensors, whatever a tensor is, I don't care right now, frame Fi, Fj of the bilinear form. And if you have any vector bundle in a frame, and any dual bundle, for the dual bundle, you have the associated frame for the associated bilinear form. This is complete general, right? Okay. Now, this word, I didn't learn much Latin in high school, but I learned that word because I grew up in a capitalistic country named United States, and you learn in the United States, caveat emptor. So emptor means buyer, to buy something. You speak Latin? You can speak Latin to me if you like. Caveat emptor means you look out, the buyer beware. That's what you say in English, buyer beware. This means if I want to sell you something, I can cheat you, it's your problem. Now you have to watch out. That's the big capitalistic thing, which I don't like, of course. Okay, so caveat here. What is a caveat? I can't even remember what the caveat is. What do I want to say? I get upset with capitalism, and I can't even think what I wanted to say about caveat. What was I talking about here? I'll think of it in a minute. Oh yeah, caveat. Not every bilinear form is non-degenerate. So a signature of a bilinear form is invariant here. So the space of bilinear forms decomposes based on signature. Based on signature. I know there are some fancy ways to write signature, but I always write the non-fancy way. P, Q, R. That means this maximal positive space is p-dimensional, the maximal negative space is q-dimensional, and the degeneracy is r-dimensional. Okay? I like to do that. Just write it all out. Why not? You can write index and all of these things here, but I just write all the positive here. Be careful. Be careful. The maximal positive space is not at all unique. There's no such thing as the maximal. I just said it, but there's no such thing as the maximal space, positive space. You move it a little bit and it stays positive. Right? Everything's continuous. And in fact, yeah. So you have a cone where you have these stable things. This number R is of course canonical. This degeneracy, that's a canonical invariant, but the various spaces themselves are not canonical. So, and here we discuss well, I can see that I've forgotten what I'm really discussing. So here we discuss symmetric bilinear forms. Bilinear forms. Where the signature makes sense. I'm sorry, you can discuss any bit of bilinear forms, but I'm discussing symmetric bilinear forms. So, right, this is completely clear. Right? So you understand what I mean by symmetric, of course. B of u v equals B of v u. Okay? So that is Riemannian type geometry. And here's another caveat. Other types of forms are very important. And the one I find most important is antisymmetric. Okay. So in Riemannian geometry, or in the case of pseudo-Riemannian geometry, we are talking about symmetric forms. Symmetric forms. So in the Riemannian case, or pseudo-Riemannian case, we're talking about symmetric, non-degenerate. Now on, I really mean that when I say that, okay? Sometimes I forget to say it, but symmetric, non-degenerate. And quite often then I will write the norm of a vector squared with respect to b as b u u. And if the form is positive and definite, this will always be a uninorm in the classical sense, but if it's not positive, this may be negative. And that's okay, it's allowed. Okay? Fine. Let me just make a remark to remind you of something. The first easy technique in this subject is that we always use, and you never should forget, is Gram-Schmidt. I guess it's Schmidt or Schmidt. Who knows whether Schmidt or Schmidt? DT at the end? DT at the end, so Schmidt. It's pronounced differently in German, you know. One is Schmidt and one is Schmidt. I don't know, do you agree? You don't agree? Okay. There's a very interesting mathematician at Harvard, a friend of mine named Wilfried Schmidt. He's careful to pronounce it almost like Schmidt. Very precise. So Gram-Schmidt is the funny. If you're dealing with forms, Gram-Schmidt is one of the most important things, right? Just remind you of the fact. You start with a vector, take an orthogonal complement, take a vector there, take an orthogonal complement, and so on, and get orthonormal base. Fine, so then if you have a frame E, maybe even I take it of the tangent bundle, and that's the frame of the tangent bundle. Then we go over to this dual frame. I don't know, call it that. Well, we know what it is, dx1 through dxn of the cotangent bundle. And then you go over to the frame dxi tensor dxj of the bundle of bilinear forms. On the tangent bundle. So that says you have the smooth structure, so you have the locally a bilinear form, a section of that bundle, of this bilinear bundle, and this bilinear bundle, and a tangent bundle. Any vector bundle, but I talk about the tangent bundle, can be written as equals Fij dx tensor j. Yeah. That's what it is. That's any bilinear form. But of course we're dealing with symmetric bilinear forms. Right? So we introduce a notation, the classical notation for symmetric bilinear forms. So, symmetric bilinear forms, symmetric means basis is this, and this is the usual notation dxi dxj. So it's symmetric in general, it's just fi fj. When you see it in books, fi fj, that means the symmetric, without a tensor, it means the symmetric bilinear form fi fj. So in our case, dxi dxj. Okay? And what that is, it's the symmetrized form dxi dxj. It's the same thing as dxj dxy. And it's the average form dxi tensor dxj plus dxj dxi. Okay, that makes it symmetry. Okay. So when you see that, okay. So for example, what I used to do in high school, and what you see all the time, if the manifold is R2, I had to do this in high school all the time. I liked it very much, actually, fooling around these forms. With the standard coordinates dx and y as the coordinates, then it's globally, you have a global frame. So you have a global frame, the global frame is dx squared, dxy, dy squared is the global frame. Right? And the bilinear form then, and I'll dedicate it to Gauss, is dx squared, with a constant of course, a dx squared plus 2b dx dy plus c dy squared. We always write it that way, and of course that corresponds to the basis, in this basis of arbitrary forms, as a, b, b, c. Right, so it corresponds to the symmetric matrix a, b, b, c, right? And this is the form. So for the plane, these bilinear things, these global, here's a global frame. I mean, here they are. Here are all global, yes ma'am. Yes.
Does the number of elements in the frame have any meaning? Is it constant, or I mean, why do we have x and y, which is like two coordinates in the basis, and the dimension is 2? but then when you have the frame, you have 3 elements. Is it?
If it for R, what do you mean you have 3 elements? For R2 I only need 2. Why do you say that?
Yes, so why is it the x squared, the x dy, and dy squared? So that's 3, right?
Yeah, that's corresponding to the fact that the space of bilinear forms in 2 dimensions is 3-dimensional.
So the space of the
Because it's the symmetric matrices.
So is there like a formula for the space of, for the dimension of the space of bilinear?
Yes, I just told you. It's the dimension of the space of symmetric matrices. Okay? And you know it, so you know what it is. N by n symmetric matrices, you can prescribe the diagonal arbitrarily, and then anything above diagonal arbitrarily, and then everything's determined, right? So let's just, dimension over R of the bilinear forms on a vector space, and that will be the fiber of the bilinear bundle. So this bilinear bundle in dimension jumps incredible, but jumps quadratically. So that's what I think that's what you're asking. This thing is right? And n degrees freedom in the diagonal, n minus 1 and just above the diagonal, and so on, right? And that's it. Right? So it's n plus 1 times n over 2. Okay? That was your question, right? Thank you very much. So it's very nice. You start with a vector bundle of rank n, dual bundle rank n, and you jump to a bundle of well, it's a bundle of matrices, if you want to think of it in this case. Okay, any other remarks? That's good. Okay. All right. That's what a symmetric bilinear form looks like. You see people writing this, and you've seen it in calculus probably. Yeah, remember, let me remind you of your calculus course. Calculus. You, for some reason in calculus, probably wrote this. Right? And that means, what you see, what this thing means here, if you apply it to a vector, g of uu is the norm squared of this vector with respect to g. Okay, that's the norm squared of the length of the vector. If you use this bilinear form on R2, this is, of course, the standard Euclidean geometry. I could never understand that when even later, when I was your age. What is ds? What is ds? It's that. What does it mean? If you want to measure the length of a tangent vector, norm, squared, so if t is v is if v, yeah, here we go, here's a curve, here's a tangent vector v, and the length of v squared is g of vv, and in the standard geometry is d x squared plus dy squared of vv of vv, and if v is equal to vx vy as a vector, then the standard, this is just this length of v squared, the length square root now is just the square root of v squared x plus v squared y. Right? You're you don't like this. You're okay on it? Good. Okay. So that's what you did in calculus, right? And anybody, these physics are laughing, these physics people are laughing because they do this all the time. But remember, you compute the length of a curve gamma as integral from the beginning, say at 0 to 1, is parameterized by time from 0 to 1, and with velocity of x, so gamma is equal to x of t, y of t, gamma of t is equal to x of t, y of t, and then then you have to find the length of it. Okay, so we just add up the lengths of the tangent vector. You did this in calculus. Is x dot squared, that's the tangent vector, t times t, plus y dot squared times t dt. Your teacher in calculus told you to do that in high school, right? You add up the lengths of the tangent vector. You're adding up with the bilinear form, which is not moving, it's constant. That's the advantage you have here. It's a constant bilinear form, constant geometry, constant Euclidean geometry. You find the length of this thing as well. Okay? So it's a little bit of a hint at what we're interested in, but I never understood it. What the heck is ds? I don't know what the heck the square root of a bilinear form is. I really don't know. But I know what the bilinear form means. So it just means, its square root just means this, right? It means you're computing. It means you're computing the middle. Okay, so that's the thing. And we have then definition of pseudo-Riemannian metric. On M is a section B, let's call it G for Gauss, G over the manifold M of the bundle of bilinear forms on the tangent bundle, which is symmetric, is non-degenerate, symmetric, and non-degenerate. The word pseudo, maybe I should not use in this context, but let me just say, I will use it very quickly. If it's positive definite at each ax, and of course it's enough to have it at one ax, because it's never degenerate, then G. Then G is called a Riemannian metric. So far we have M. And when we have M, we have sections of vector, we have vector bundles on M. Certain important vector bundles. We have sections of these vector bundles. We have the associated bilinear form bundles. And we have sections of the bilinear form bundles. And a guy here is called a bundle metric, a bundle metric on the bundle. All of this is for us nowadays a complete triviality, right? I mean, it's just bilinear forms, there's no problem. I think it was very difficult for Riemann. Okay? So you have bundles and you have bundle metrics, and these are the fundamental things at first in this subject. So that's a sort of a formal introduction to my lecture today. Are there any remarks? I made some stupid things here. This is pretty formal, right? It's not very interesting, but we need to get these things down. I've tried to indicate in these lectures so far, and I think maybe I've exaggerated. I apologize. My usual problem, I exaggerate. My wife tells me this all the time. But the key, for me, the key first idea after the above is that of a connection. On a vector bundle. And I introduced this to you this morning, and it really probably made you mad because it was too abstract for you, but I think if you keep saying it over and over again, it's not so bad. Right? You have R as a ring, maybe I'll just write a script, so a commutative ring. And when you write that, you just say, think about functions. See infinity functions. And M is an R module. And you should think about sections in a vector bundle. Right? And then you have a mapping, which is the definition of the module structure, maybe is given by Rm. It's just multiplied by M. It's the same axioms as vector space, except you're multiplying by things like functions, and it's not scalars. Okay? And when you have any ring, anything, any place where you can multiply, you have any place where you can multiply, you want to know what Leibniz would do. This is 1627 or 30, whatever, Leibniz was a young boy. Leibniz, what are you going to do with that ring? And he says, a derivation d on this ring. D is a derivation on this ring. On this ring means that, and I even write it in my, you see, my good friend Ivan Penkov, if I write F, he never has written F for an element of a ring. All right? I always write it because I want to think of a function. Okay, D, I just say, what would Leibniz say? He would say this. Okay, so that's what a derivation is. And now you want to know what goes on at the level of the module. Okay? So a connection takes derivations on the ring into first order differential operators on the module. Basically, derivations on the module. You know how to take derivatives on the ring. You want to know how to take derivatives on the module. Right? This should be an R linear map. So we call that an R module morphism. Yeah? And the statement is, if you map over an element of the derivations and apply it to a function times an element of the module, then it's just the function derived, a function times the derived element of the module, plus the derived function, which you already know, times the module element. This is the appropriate Leibniz rule in here. Okay. That's what a connection is. That's all a connection is. Okay. Now I guarantee you, if you walk down the street and meet mathematicians who are supposed to know what a connection is, and you say, what's a connection? They will not be able to define it. Right? This is the only definition. It's an association which is compatible with the module structure to a vector field, for example, to a differential operator, first order. What else do you want? Okay. So that's a connection. And C of the vector bundle over the manifold is the space of all connections on. And the notation is, of course, I try to use classical notation if possible. It's, you take, so X is mapped over to this differential operator, which we call nabla of X. So instead we don't write nabla of X, we write nabla sub X. I don't know who introduced that notation. You use it in physics also, right? Oh, it's downstairs, or not?
You don't write the vector field.
Huh?
You don't write the vector field.
They don't even write the vector field. What do you write?
There's nothing, so the vector field later you can have.
Well, they're fantastic. They understand so much they don't need to write anything. So it's fantastic. That's wonderful. And it is true, the physics notation is usually very, very good. Okay, so that is what we're studying. I've really made a huge discussion of this. So if this is a frame, of the tangent bundle, then all you need to know is what the connection does on the frame. And so you say, what does the connection do on the frame? Well, it differentiates vector fields, so it differentiates vector fields. And the answer to it is a vector field, and every vector field is a linear combination of the frame elements. So this is the definition of the Christoffel symbol gamma ijk. That's the definition of the Christoffel symbol. I don't particularly like that definition, so I do a little slightly different definition. Something like maybe if X is a vector field, and then nabla X, well, I need to know what nabla X does to delta, that should be del I, and this is a linear combination applied to X. This is a linear function applied to X, delta J. And this is the same thing as here, but I just, where this omega ij now is a matrix. See, this is a matrix operating on these vectors, is a matrix of one forms. It's exactly the same thing as the Christoffel business, except I use one forms here. So, and it's quite often used nowadays in mathematics. So, this is called the connection matrix. That's an omega. So I've spent close to 40 minutes reviewing, but I don't object to it. And one major goal of this that I think Bremen understood very well is a new notion for us, which is called parallel transform. via the connection. Okay. So what is this? What's the picture that you need to know? You have a curve starting at time 0, x0. This is, say, gamma of 0. And you have this curve. And actually, it's any curve, but let's just draw it as a simple curve to another point, x1. And you want to know what it means to start out with a vector here, which I will call y, and transport it along this curve, parallel along this curve, what it means to be parallel along this curve, and end up with a vector here. Well, at any time t, you get a vector field along this curve, which we will call parallel transport from 0 to time t by the curve gamma of the vector y. You hate me for this notation? Yeah? I start with a vector at the base point. There will be a way of transporting it parallel along this curve. And a vector is an element of the fiber of the bundle at the base point, whatever the bundle is. It's a vector here. I transport it parallel with respect to this connection along this curve, and at time t, I get this thing, and what I end up with is a vector field along the curve, which is parallel at all points. You understand the words anyway. Right? Yes?
I have one question, but it's really about the connection matrix.
You're not loud enough for me. What?
How does one determine the connection matrix? Like, is it some abstract thing, or is it something that you can determine?
Okay.
Well, what is
You're back in the first. That's I don't object. You don't. Yes. I explained to you something called a connection. I also explained to you, and I didn't explain it today, but I explained to you the difference between any two connections is really some very simple thing. This derivation thing goes away, right? So it's just some huge space of connection, some huge affine space. Okay, so, and you can make it with partition unity and so on. I explained all of that, right? So it's very easy to make connections. That you can tell you're trying to make a connection with some friend of yours. Just say it's very easy to make a connection. I know this lingo nowadays. I've forgotten what it means. I'm so old. But okay, it's very easy to make a connection because you have this freedom with partition of unity and so on, right? So there's some huge space of connections, okay? And I think you didn't formulate your question the way you wanted to. I think what you mean is, what is a good connection? How do I get a connection? Or yeah, that's what you mean. That's a very deep question. The question says, in some, for example, physical situation, what is the right connection? Because as you will see, I hope today, connection is closely related to curvature. It gives you everything you really want to do on this manifold. But it has to be related to the application you have in mind, right? It's not just something. So right now, it's a very, I'm happy about your remark, but it's a very weak thing, because I'm just saying, just take any connection, and there it is, and I use it. So I just made this statement about parallel transport along a curve of a vector using the connection. And I should not say using the connection, because there's no such thing. I should say using a connection. And some connection. Okay? You're cool with it, right? Okay, good. So whatever that means, that we want to understand what it means. So for this, we need a definition. So let's let S be a section of the vector bundle defined near the curve gamma. So here's the curve gamma. Here it is. Here's a point gamma of t. Here's a tangent vector gamma point of t. This is all in a local coordinate, say. In local coordinates. Okay, so we have a section, and now you have a section here, section at gamma of 0. Maybe we call this S sub 0, and here is maybe right here, section at gamma of t, and maybe at the endpoint, is section of gamma of 1, whatever it is, on this curve. So we have a section along this curve, and we draw it as vectors. Okay, they are vectors. Yeah? It's in a local coordinate system, they're vectors in urban space. We say S is parallel along gamma if the derivative of the section is 0. It doesn't move. It doesn't move with respect to gamma. Well, that's what constant means. Right? That's what it means. Constant, the section is constant along gamma. It doesn't move. It means its derivative is 0. What in the devil does it mean its derivative is 0? That is not abstractly defined, because don't forget we're talking about its derivative here, here. It means the derivative with respect to the given structure. The given structure is the connection. Right. In the Euclidean connection that we just talked about here, parallel means actually parallel. Okay? You can prove it very easily. Parallel here is a very deep, complicated notion, but it makes sense from the point of view of differential operators. Right? It's just parallel with respect to that. This is not a vector field on this, so here gamma point means a vector field defined, a vector field defined near, let's call it X, near the curve. So what that means is that along the curve you have the velocity vector of vector field, this is gamma point. At least you know what it means in coordinates, and so on. This is what it means in coordinates, gamma point. And I write this as, and then near here, I push this vector field, I extend it here transversely in some way so that it's defined in a neighborhood. You can imagine how to do that, right? You just take transversal and then push it transversally in a neighborhood. You see what I mean, right? Right, that's good. So you extend, you can always extend this gamma point, which is only defined along curve, to a vector field X, and it means, so this equation star means simply that nabla X of S is 0 on gamma. You understand what I'm saying? Nabla of X is only defined when X is a vector field. And if you just have it along the curve, it's not even defined. So you just push it off the curve in an extended way. Right? Okay. So, and then I'm speaking over it. Okay? And then we say S is parallel along this curve. Okay?
Question, what if the curve self-intersects?
Okay, so you have to really start to think about what it means, a self-intersecting curve. And the right curves here to consider at first are not such, but are piecewise smooth with no self-intersections. Okay? And you really, and in fact, your textbook talks, I didn't want to get into it right now, but you really need to think, because about what such a thing is. For geodesics, when you're talking about geodesics, it's sufficient to talk about piecewise smooth and no self-intersections. But just like Misha, I would like to be able to introduce a theory for any smooth curve, right? And so, so in your textbook, I checked it because I know you might be interested in reading. The author discusses admissible curves. When an admissible curve means piecewise smooth, no self-intersections. Okay, and then Misha, you understand, of course, it's very easy to push some vector field off that curve, right? Okay. So with respect to C in the text, for the notion of admissible curve. Okay. So let me just prove a theorem for you, and then we have a little pause until the next session today is given y in the tangent space at the base point, no, not in the tangent space, any vector at the base point. There is a unique vector field gamma. So gamma y of t, which is in the vector bundle of gamma of t. Let me write this here as gamma of 0 and gamma of t with, which is parallel along the curve. So that means gamma of y of t is 0. Okay. That's a first start. That's not bad, right? You give me a curve and an initial vector, and I can give you, using the connection, depending on the connection, of course, a canonical movement of that thing parallel to the other end. From the beginning to the end, parallel. Okay. This is what Riemann was feeling. It's called parallel transport. Okay. Good. Let me prove it. This is well known to you, but you didn't realize you knew. Oof. Okay. So let's let y and t, so let's prove it using a local frame first. E, say E1, QEN. 4. E. So we want this thing y of t should be then functions f I of t e I of t. where the fi's are to be determined. Okay? And the condition is that nabla of gamma point of yp is 0 is the condition. You need to understand. Okay. So gamma point of t, that's a vector field, so that's the vector field x. Let's call it xi di. Well, all of this is dependent upon t as we move along the curve. So maybe I write it xi of t di of t, of course. Okay. Well, okay. So what is the condition? Let's write this as star, and let's write it out. So star is this guy applied to that guy means first you differentiate. First you get fi. Oh well, here we go again. Let's call this one is I and one is j. I knew I was going to make this mistake. Let's call this thing j, and let's call this thing I. Right. And now we hit this thing with this differential operator, and the first thing we do is we pull out fj of t, and we apply the basic frame to the basic frame. Right. This is what's going to be the Christoffel symbol. If this for the tangent bundle, this will be Christoffel symbol. So omega appears. That's the first thing you do, is you pull out the constant and you apply. Did I do everything? I pulled out, here's y, and I pulled out this thing, that's fine. And now what I have to do is I have to differentiate this thing. So this is the partial derivative of fj with respect to di times what? ej. Right? Have I done it right? Please check me. Right, I applied Leibniz somehow, right? So I apply this guy to that guy, and what I do is, the coefficients here, I didn't even, I'm an idiot. Okay. Where? Here I need coefficients, right? xi. Well, I mean, and this has to be 0. Okay. Right? No, that means it has to be 0 for all j. It means this has to be 0 for all j. fj of t.
You're still missing xi.
Huh?
You're still missing xi next to the f.
Next to the what?
So we're taking so the connection and the vector field you just showed.
Here's the vector field.
Yeah, so the left.
And here, I forgot the xi here again also, right?
Yeah.
xi. Okay? Right?
Yeah.
So let me write it down. So what I have to do is fxi delta I plus xi. I'm probably making a mistake here someplace, but it doesn't matter. Has to be equal to 0 for all j. Right? Because that's a basis of the vector space, so all the coefficients have to be 0. Right? Well, look at that for a minute. Okay. Notice that these are the unknowns, and this is a linear in these unknowns. This is just something I don't know what that is. And here are the derivatives of the unknowns. This is what is known as the standard ODE. So this is a standard ODE, a first order ODE, and you apply the standard existence and uniqueness of the standard ODE, which means for any beginning initial value of the functions, you have a unique solution. Well, the initial value here is y of 0. So you have a vector y of 0 in the bundle, and you push it with this differential equation, and you have a unique solution which is called parallel transport. Okay. So, and you can believe me that the other way around, parallel transport is very, very close to a connection. So you can see how Riemann was thinking of moving from one fiber to the other in the bundle. So this is parallel transport. Okay. You okay? Yeah. Okay. That's perfect timing to finish the lecture. So we meet again in what time? 15 after or something like that. Thank you. So I hope you can hold out these 3 lectures in one day. We'll see what happens.